In this course, we will learn the basics of Jupyter Notebooks, its features, and its uses in data cleaning, transformation, visualizations, and machine learning. Jupyter Notebook is a web-based interactive environment that enables users to combine code, images, videos, text, equations, or plots or maps, and other interactive figures and graphical user interfaces into a single unified document. These notebooks are easy to share as they are saved as structured text files, which is the JSON format. They can be easily converted to other formats such as HTML and PDF using easily available tools online, and also give the user the flexibility to easily render available notebooks directly on a browser. An interesting aspect of the Jupyter Notebook is that the architecture is completely language independent, which makes it possible for users to write kernels in any language. A notebook kernel is the computational engine that executes the code within a notebook document. For Python code, an IPython kernel is used to execute the Python code. Similar kernels for other languages also exist to execute code in Jupyter Notebook. However, for the duration of this course, we will be using IPython kernel. Jupyter Notebooks are very easy to customize and allow the users to create custom interfaces along with creating extensions that make using Jupyter Notebooks even easier. The Jupyter Notebook application is used for data cleaning and transformation, creating statistical methods, numerical simulations, data visualizations, and used in machine learning. These notebooks support data tools such as Apache Spark from Python, R, and Scala. Jupyter Notebook have integrated tools such as Voila, which helps the users to communicate their insights by transforming Jupyter Notebook into a standalone web application that can be easily shared and enables the user to create a customized experience and an interactive dashboard for their readers. The notebook consists of documents produced by the Jupyter Notebook that contain both executable computer code as well as other rich text elements such as text images, links, etc. Therefore, notebook documents can be read by people as well as contain executable elements which can be run to perform data analytics. In consequent courses and demonstration, you will see glimpses of these features of Jupyter Notebooks in action. In this course, we will get a short Python refresher or introduction. Also, we will get introduced to various packages in Python that are commonly used in data analysis. Python is a general-purpose, interactive, object-oriented, and high-level programming language that has become the de facto standard for data science computational applications. It is designed to be a highly readable language, which uses a lot of English keywords. It also has fewer syntactical constructions compared to other programming languages. It is an interpreted language, which means that it is processed at runtime by the interpreter and there is no need to compile the programs before execution. It is interactive and object-oriented, which enables the users to encapsulate code within objects. Python is predominantly portable and has cross-platform compatibility on various operating systems. It can be run on different hardware platforms and has the same interface on all platforms. Python also supports graphical user interface applications on various operating systems. It provides an optimized structure and support for large and scalable programming. Numpy is one of the most fundamental packages in Python, which is used for array processing as it facilitates math operations on arrays as well as their vectorization, which significantly speeds up the processing time. Pandas is another fundamental package in Python, which is an open source package providing high performance and easy to use data structures and data analysis tools for labeled data. It helps users to quickly manipulate data, read or aggregate data, and also to create basic visualizations using the data. Matplotlib is a package in Python that provides a library to create visualizations such as line plots, bar charts, histograms. It also enables users to add labels, legends, and other visual communication elements. Seaborn is another visualization library for Python for creating high-level and informative statistical graphics. It is essentially an extension of Matplotlib with advanced features. Scikit-learn is the machine learning library for Python that contains machine learning algorithms such as random forest, k-means, SVMs, etc. It is often used to deploy a range of supervised and unsupervised machine learning algorithms used in an interactive interface in Python. In this video, we will get briefly introduced to Numpy package and how it's used in data analysis. Numpy stands for Numerical Python, and was created as a centralized library for working with arrays. It also has functions for working in domains of linear algebra, matrices, and etc. Traditionally, Python has lists that can serve the purpose of arrays but are very slow to process, something which NumPy addresses by providing an array object that is up to 50 times faster than a traditional Python list. The array object in NumPy is called NdArray and has a host of supporting functions that are very easy to work with. NumPy are stored in singular continuous place in memory, unlike traditional Python lists, so processes can access and manipulate these NumPy arrays a lot more effectively, therefore making the process faster as it is optimized to work with the latest CPU architectures. NumPy libraries are predominantly written in C or C++. NumPy supports various data types such as integer, boolean, float, unsigned integer, time delta, datetime, object, and string, amongst others. Users can create arrays with a defined data type, convert data type on an existing array, check whether arrays have their own data, check the shape of an array, combine or split arrays, and many such features. NumPy also enables sorting of an array in ascending or descending ordered sequence where the values could be numeric or alphabetical. In this video, we will get briefly introduced to Pandas and how it's used in data analysis. Pandas is a library used for data manipulation and analysis in Python. It provides users with data structures and operations used for manipulating numerical tables and time series data. The name Pandas is derived from the term panel data, which is a term used in econometrics for data sets that have observations spanning multiple time periods for the same attributes or individuals. The main feature of the Pandas library include data frame, which are object for data manipulation with integrated indexing. It has inbuilt tools for reading and writing data between structures and with different formats. It allows users to align and manage missing data, filter datasets, or index datasets. It also allows users to slice or create subsets from large datasets based on different labels. The Pandas library also has time series functionality, performing moving window statistics, generating date ranges, and converting frequency of data. Pandas allows users to import data from different file formats such as CSV, JSON, SQL, or even Microsoft Excel for performing data analytics and data cleaning. In this video, you will have an overview of Jupyter notebooks running on Python with NumPy package and with an on-screen demonstration. With Python 3.8 running on our local machine and with pre-installed IDE for Python, we will first install the required packages including Jupyter Notebook and NumPy. From there on, we will learn how to create a new Jupyter Notebook and then we will review some code for NumPy on an existing Jupyter Notebook. So let us get started. First, let us open the terminal window on our IDE to install required packages. If you're running PyCharm, the terminal window option is on the bottom left of the screen. First, we will install Jupyter Notebook with the command pip install Jupyter. On pressing the Enter key, all required dependencies will be installed for Jupyter Notebook package and the Jupyter Notebook itself. Since I would have installed all the dependencies earlier, the requirements were already satisfied on my machine. Similarly, we can install Pandas and NumPy packages. We can first install Pandas package by the command pip install pandas and press the Enter key. One of the dependencies of Pandas package is the NumPy package itself. So we could skip installing NumPy package as it would be already installed with the Pandas package. Just to be sure, you could run the pip install numpy command on your terminal window and see the output. Now that all the three packages are installed, we can start off with running the Jupyter Notebook. First, let us clear the terminal screen by running the command clear on the screen. Jupyter Notebook can be run and installed in multiple ways. In the method that we've used to install Jupyter Notebook, we can simply type in the relevant command in the terminal window. The command will be Jupyter space notebook. On pressing the Enter key, the Jupyter Notebook will be opened in a new tab in your browser. As we can see, there are some existing files in this Jupyter Notebook, and one of the files stored with .ipnyb extension. This is the extension that Jupyter Notebook uses to save its files. The code files can be shared as just another document and can be opened and run on any instance of a Jupyter Notebook. To open a new Jupyter Notebook, we can simply click on the menu button on the top right of the center table. Now, this opens a new notebook. However, for the duration of this video, we will be reviewing the code in another pre-existing notebook. In order to open an existing notebook, you can go back to the home screen opened on another tab and click on the file name you want to open. In order to use Pandas and Numpy packages, we need to first import them as Python objects. Under the Import Packages header, we've just done that. If we look at the first cell under Import Packages header, we've imported Pandas as PD in line 1 and imported Numpy as NP object in line 2. So let's run this cell. Once the packages are returned without error, we are now ready to review the code for Numpy package. Let's begin with reviewing the Numpy codes first. Here, we will first look at the difference between a Numpy array and a Python array. Then we will create a 3D array and check its dimensions. Then we will access these values in the 3D array. So first, let's have a look at how to create a Numpy array. In the selected cell, the first cell under Numpy header, we have created a Python array in the cell number 2. The array is contained in square brackets. Whereas in order to generate a Numpy array, we have to type in the command np.array before defining the array. First, let's have a look at Python array. This array has values 1, 2, 3, 4, 5 in square brackets. The output of Numpy array looks similar to the Python array, except it's preceded by a keyword array as shown in output cell number 3. In the next cell, we will check how Numpy and Python arrays are stored in memory. Referring to the output of cell 4, we see that Numpy array is stored as numpy.nd array, whereas the Python array is stored as a list object. Next, let us create an nd array using Numpy. We will be creating a random array as described in code line number 2 of cell 5. Here we've used np.random.randin function to describe the array. On running the cell, the output is now displayed in output cell 5. In the next cell, let us check the dimension of a Numpy array. For this, we can use the .ndim command in line 2 of the selected cell. As we can see in the same line, .ndim command is used to the Numpy array object that we created in an earlier step. Here, the object is named as multi-dimension array. On running the cell, we can see the dimension is 3. In the next cell, we can access the third dimension of the ND array. Before we look at the output of the next cell, let's recreate the random ND array by running 2 cells before the current cell. Finally, in cell 12 and line 2, we've used the mean summary statistic command to view the average of one of the third dimension of the random ND array that we had created. For many other cases and features of Numpy, it is advised that you use the Numpy documentation that is easily accessible online and is well maintained. In the next video, we will learn some features of the Pandas package. In this video, we will review some existing code to learn and understand the features of Pandas package. We will be reviewing some applications of Pandas package, such as reading the data or loading the data from a CSV file, understanding the data and understanding the summary statistics of the loaded data, and transforming the data. There are many more such applications of Pandas, but we will be covering just the 3 of these today. To store data, Pandas uses a table-like object that is called data frame. We can create this data frame from using an existing data in .csv file, or we can import it from SQL, MongoDB, or maybe in JSON format, or even as a list. For the purpose of this video, we will be using a .csv file to create a Pandas data frame object. So let us review the code on screen now. In the selected cell, code line number 2, we have used the command pd.read_csv with the file name in parentheses. By running the selected cell, the data will be stored in a data frame object called input_data. Similarly, we can create a data frame object from other formats such as SQL, MongoDB, and etc. Now, let us move forward to view and understand the data that is stored in the Pandas data frame object. So let us follow the code under data understanding and summary statistics. To view the size of the data frame, we have suffixed the .shape command to our input data object in the selected cell. In the output cell 15, we can see that the result represents 565 rows and 7 columns. In the subsequent cell, we have suffixed a .head command to our input data frame object. The result displayed in the output cell 16 gives the top 6 rows of our data frame, including the header row. also are the 7 columns with date being the first column. Similarly, we can view the bottom 6 rows of the data frame object by using a .tail command as we have done in the subsequent cell. The output is shown in the output cell number 18. Now let us see some statistics of our data frame in the subsequent cell. The returned table in the output cell 19 describes a statistical summary as depicted by the row values of the table. To retrieve the statistics table, we have suffixed a .subscribe command to input data as shown in input cell 19. Now, if we look at the last column of the resultant table, we will notice that the range of the column is 0, as the max and min of row values columns are 0. As the 0 values in the volume column are not adding any extra information to our data frame, we will remove the volume column in the next section. Under the data transformation section, we will review some cleaning functions as well as some functions to add extra attributes to our data frame. So let us review the code under data transformation header now. First of all, we will remove the volume column from our data frame. For that, let us select the fourth cell under cleaning header. Here, we have suffixed a drop command to our input data frame and given the appropriate values as its parameters, including the required column name, axis, and given in place underscore true. To confirm that the column is deleted, let us scroll up and rerun the cell that gave the statistical summary. In the resultant cell 21, we notice that the volume column is absent from the data frame as desired. Next, let us find out whether our data frame has any null values. For that, let us review the code in the first cell under the cleaning header. In the code line number 2, we have suffixed isNull and some commands to the input data, where isNull command would return the true Boolean values where the values are null. As a result, we would get the number of null values in the data frame. When we run the selected cell, we notice that in cell 22 the attributes open and high have 1 null values each. To confirm that's true, we have displayed the rows with null values in output cell 23. In the subsequent cell, we have suffixed drop NA to input underscore data to delete all rows with null values. Empty result is displayed on running cell 24 because we have given in place is equal to true with drop NA command. To confirm whether the rows with null values are removed, we can run cell number 22 again. In the resultant cell, that is the output of 25th cell, we can see that there are no null values under open or high columns. That must mean that we've successfully removed all rows with null values. Next, let us add some features to our Pandas data frame object. Pandas allows us to add many complex features to our data frame object. In our case, we will be adding 3 types of features to our data frame object. First would be the static feature, which would mean the same value is added to all rows of the data frame object. Second would be the computation feature, wherein values in the new column will be based on values in other columns. We will shortly see how that works. The third type of feature would be a little more complex, wherein we would be calculating the average of previous 5 values in one of the new columns that we have created. So let's begin with adding a static value to our data frame object. In code line 1 of input cell 26, we have given a command to create a new column. The column named type is suffixed to input underscore data in square brackets. We have made this column equal to the text value VIX. The desired output is then shown in output cell 26. In the subsequent cell and code line number 1, we have followed the same syntax as in the previous cell to add a new column. This time the column is called range. Here, we have made the new column equal to the difference of column high and column low of the input underscore data frame. The resultant table then can be viewed in the output cell 27. In code line 1 of subsequent cell, we have suffixed a column named 5 underscore day underscore range underscore mean in square brackets to the input underscore data frame. And we have made this equal to the 5-day rolling mean of the range column. In other words, each row value in the 5-day range mean column would be the average of previous 5 values of the range column. On running the cell, we can review that such a column is added to the table in output cell 28. Pandas can allow us many more complex features. The best way to understand Pandas is to practice it on your application and use the documentation that is available on the internet. I hope you found this demonstration useful. In this video, we will briefly get introduced to Matplotlib and how it is used in data analysis. Matplotlib is a plotting library used for Python and for Numpy. It provides an object-oriented API to allow users to embed different kinds of graphical visualizations into applications using an interactive GUI toolkit. Matplotlib has a module called PyPlot, which is a MATLAB-like interface for users with the open source and free advantages of Python. Matplotlib is used to create simple visual graphics such as line plots, histograms, scatter plots, 3D plots, contours, image plots, and etc. There are various additional toolkits that are available that extend the Matplotlib functionality. One of them is Scartop, which is a mapping feature that creates object-oriented map projection definitions. One other tool is an Excel tool, which allows users to easily exchange data with Microsoft Excel. Another such tool is Basemap, which is a map loading toolkit that allows users to create various map projections, geopolitical boundaries, and coastlines. In this video, we will briefly get introduced to a Seaborn package and how it's used in data analysis. Seaborn is another visual and graphical statistical library for Python, which is an extension of Matplotlib. It is closely integrated with pandas and data structures. It helps the users to explore and understand their data. The functions in Seaborn operate on data frames and arrays that perform the necessary statistical aggregations to produce informative plots. Its APIs allow users to focus on understanding and inferring different elements on graphical plots rather than focusing on how to draw them. Seaborn automatically performs statistical estimations on various variables that are being plotted. For example, it can compute confidence intervals and can draw error bars to represent uncertainty of a certain estimate. Seaborn also has specialized plot types which are oriented towards creating visualizations for categorical data. Instead of drawing generic scatter plots, Seaborn allows users to adjust the positions of using categorical axes and create a swarm plot so that points do not overlap with each other. It allows users to quickly create combined composite plots, which are really helpful to summarize the information in one place. Another functionality of Seaborn is that it allows creation of complex figures that link structures of a dataset to a grid of axes very easily. To understand a dataset or to make statistical inferences, it becomes necessary to visualize our data. Matplotlib and Seaborn packages in Python can allow to do just that. These packages are especially helpful if we have processed our data using Pandas or Numpy. In this video, we will use Matplotlib and Seaborn packages to visualize our data. We will work with the price data frame from the Pandas and Numpy demonstration video and use the same Pandas data frame to plot data using Matplotlib and Seaborn libraries. Before we begin, let's review the input data frame once again. In the price data frame on the screen, we have price data available for asset split by 1-day interval excluding the weekends. Here, the open, high, low, close columns are the prices for the asset on the corresponding date. Also, if you remember from Pandas and Numpy demo, we added 3 features or 3 columns, namely type, range, and 5-day range mean. For the purpose of this video, we will only work with close prices represented in the close column of the data frame on the screen. First, let's begin to understand the applications of Matplotlib. We would first start off with importing the necessary packages. Here, in cell 26, we are importing Matplotlib and MPL Finance package. Earlier, the MPL Finance package was a module of Matplotlib. Now, it can be downloaded as a separate package. Essentially, the independent MPL Finance package can also be viewed as a module of Matplotlib. In the subsequent steps, we will be using MPL Finance package to plot a candlestick chart of the data frame that we have in Pandas. For that, the first step is to change the index of Pandas data frame to date time. To put this in context, let's review the Pandas data frame that we have. In the price data frame on the screen, the column left to date column is the index of this data frame. As we can see, the index to the data frame is saved as a string of numbers, whereas MPL Finance requires the index of the data frame to be of date time. In order to create a candlestick chart in MPL Finance, we need to first prepare the data in our Pandas data frame. To do that, we will replace the index column with the date column in our Pandas data frame. Let us now review the code that will make this possible. In the output cell 27, we can see that the index of this data frame on the screen is replaced by the date column. If we look at the code in line 1 of cell input 27, we can see that the index is being replaced by the date column in the set format. Now, after line 1, since the index has been set, we can drop the date column in line 2. The third line in the cell 27 is just to print the data frame. Now, our data frame is ready to be used with MPL Finance package. In the next step, let's plot the candlestick chart. Now, if we run the next cell in the sequence, we would be able to plot the candlestick chart. Before we plot the chart, let's first review the code. The Python object MPF represents the package MPL Finance. MPL Finance has a plot function wherein if we give the data frame and the type of the chart to be plotted, it will display the corresponding chart. Here we've given the type as candle. Now when we run this cell, we will see that a candlestick chart is plotted. However, we can see the candlesticks are not very clear in this chart. What we can do is play around and change the features of this chart to make it more visible. We will run the subsequent cells to do just that. In the subsequent cell, we are plotting the candlestick chart by using a pre-existing style in the MPF package. Here, the style used is what is used on Yahoo website. Here we can see the candlesticks are too closely packed to make sense. What we can do is just plot the first 100 rows to make it more readable. In the next cell, let's do just that. Now, this is a more readable chart. So this is one of the very basic functionalities of the finance module in Matplotlib. On the internet, you can research for other available modules in Matplotlib as per your requirements. Next up in the demonstration, we will use Seaborn package to make statistical visualizations. Seaborn is built on top of Matplotlib, and that provides many API endpoints to visualize hard things easily. As we did for Matplotlib earlier, we first have to import the Seaborn package. We are importing the Seaborn package as a Python object named SNS. Other than that, we are also importing a math package that comes in with your Python, and we are importing pyplot module from Matplotlib as PLT. So let us run the cell that imports the package. First thing we want to see while exploring any dataset could be the distributions in the dataset. In our case, we are interested in displaying the frequency distribution of close prices. The code cell after cell 32 would do just that. The cell number 33 displays the frequency distribution of close prices. This was achieved by using the histplot function of the Seaborn package. If we look at the cell in 33, we can see that we are using histplot function of the Seaborn package. In this distribution, the x-axis represents the close prices, whereas the y-axis represents the count of those close prices. However, the frequency distribution of price may not always make sense. We may want to look at percentage frequency distribution of prices. So if we look at the subsequent cell, we've done just that. If we look at the output of cell 34, we can see that we've replaced the count with percentages or probability. All we've done in input cell 34 is added a parameter called stat and given it a value equal to probability. This is one of the very basic feature of Seaborn package. What I suggest you do for real use cases is first figure out what really you want to display on the charts. Once you have deciphered or imagined what you want to achieve in a chart or a plot, you can go onto the internet and look for relevant packages along with the relevant functionalities. With some practice of using Seaborn and Matplotlib packages, this will become very intuitive to you. In this video, we will learn about the Scikit-learn package in Python. Scikit-learn is a machine learning module in Python for ML applications such as classification, regression, clustering, model selection, and etc. Scikit-learn is a machine learning library for Python for supervised and unsupervised learning algorithms. It is built on Numpy, Pandas, and Matplotlib. Scikit-learn provides users with simple and optimized tools for performing predictive data analytics through machine learning algorithms. One of the main functionalities for Scikit-learn is to use it for linear and logistic regression for predicting a continuous valued attribute associated with an object. Another of its functionalities includes classification. Classification is identifying which category a certain object belongs to. Different classification models are already included in Scikit-learn package. These models include k-nearest neighbors, random forest, and many more. Another of Scikit-learn functionality is to use it for clustering. Clustering is automatic grouping of similar objects into sets. One typical application of clustering is customer segmentation. Another functionality of Scikit-learn package is model selection. Model selection helps users to compare, choose, and validate parameters and models. The algorithms that are already included in Scikit-learn package include grid search and cross-validation algorithms. Preprocessing helps us in feature extraction and normalization of incoming data to prepare it for machine learning applications. In one of the subsequent videos, we will demonstrate one or more of the functionalities of Scikit-learn package. In this video, we will use preprocessing functionalities from Scikit-learn to prepare the data for developing a machine learning application. In an earlier video demonstration of Matplotlib and Seaborn packages, we created a percentage frequency distribution plot. Let's study it further. The plot currently displayed at the center of the screen is the same plot that was used in Matplotlib and Seaborn package demo video. On closely studying the shape of this plot, it looks like this plot follows Benford law. Before proceeding, let us take a sidestep to understand what is Benford law. To understand what is Benford law, let us assume a dataset with numerical values. Now, as per Benford law, the leading digits of these numerical values will be stored in a non-uniform way. Specifically, the Benford law states that digit 1 will be seen around 30% of the times and number 9 will be observed as the leading digit around 5% of the times. For a graphical illustration of the Benford law, we can also refer to the plot on the screen. As it's shown, any dataset of numerical values where the leading digit 1 is around 30% of the times, the leading digit 2 of those numerical value comes around 15 to 20% of the times, and so on and so forth. If the leading digit 9 comes around 5% of the times, then that dataset is set to follow Benford law. Now that we know what Benford law is, let's revisit the price dataset that we are working with. Now, if we look at the central plot on the screen, this plot refers to the percentage frequency distribution of price data. On closely studying the shape, it looks like it follows Benford law. So, for the purpose of this demo on Scikit-learn and for an experiment, let's assume that our historical price data follows Benford law makes some business sense. If it does make any business sense, then we may want to fit our historical data to Benford law. Consequently, if our data fits well with Benford law, then we would like to run a machine learning application to estimate the range of prices at future dates. In order to assess whether we want to invest any resources on this machine learning application, we would like to first fit our data to Benford law. Therefore, in subsequent steps, we will use Scikit-learn to do just that. Let us first plot leading digits of our price data to see how well it matches with Benford law, or whether it matches with Benford law at all. To do that, let's run the cells under plot leading digits of price data header. In cell number 30 and line 4 of the code, we've created a new column or an attribute called first digit in our input data column. This new attribute stores the leading digits of the close prices. For instance, if we look at the table output of cell number 31, if we pay our attention to the first row, that is on the date 20th April 2018, if we look at the close prices, that is 16.8799, the leading digit is 1. Now this leading digit 1 is stored under the last column called first digit. Then in cell number 32, we've plotted the frequency diagram of these first digits. Let's check that out. On studying the shape of the resultant plot, we can say that our plot only partially matches Benford law. What that means is only the shape is following Benford law, not the values. We can see that the leading digit 1 occurs around 70% of the times, whereas there is not even one instance of leading digit 9. Now, before we give up our experiment, we can use other statistical tools to process the data. For instance, we can use Scikit-learn package to normalize our price data and then replot the frequency distribution and then assess whether the resultant plot matches the plot of Benford law. So now, let us proceed to pre-process our data and check whether it's fit for machine learning. Since we are using pre-processing module from Scikit-learn, we are importing just that. We are importing the min-max scalar function from pre-processing module to allow us to normalize our price data. So let us proceed to import this function. Once imported, our first step would be to convert our pandas data into something that Scikit-learn understands. Under the new variable prices, we have taken values from our close attribute from our input pandas data frame. So let us populate this prices variable. Now that the prices variable is populated, we can use scikit-learn to normalize the data between 1 and 100. To normalize the data, we are going to run the next cell in sequence. In code line 1 of cell 35, we have created a scalar object that is an initiated object of min-max scalar object from scikit-learn package. Then under code line number 2, we have run a fit_transform function under min-max scalar to normalize the prices. Then in line number 3, we have stored these normalized prices in our pandas data frame. Then, in the subsequent step, we have saved the first digit of these normalized data prices. As you can see in table output of cell number 36, there is a new attribute at the end of the table that is called first digit normalized. Now we are going to plot these leading digits of normalized price data to assess whether this follows a Benford law plot. Let's check that. On plotting the frequency distribution of leading digits of normalized price data, we can see that there are three groups of 3 bars each. This in no way follows the plot from Benford law. Hence, just by looking at the plot, we can safely say that our assumption or our hypothesis was wrong. The conclusion that we've just seen is a regular business application, where we've used Python packages such as Pandas, Numpy, Matplotlib, Seaborn, and Scikit-learn. In this course, we have learned how Jupyter Notebooks and Python can be used for data science and machine learning. We learned the advantages of Jupyter Notebooks along with running Jupyter Notebooks with Python. Then, using Jupyter Notebook, we learned how Pandas, Numpy, Matplotlib, and Seaborn packages can be useful for data science and machine learning applications. Finally, we briefly reviewed the scikit-learn package, which is a machine learning package in Python. In the next course, we will review the fundamentals of data analysis.